Within the past 24 hours, seismological instruments across the Zagros fold and thrust belt have recorded a magnitude 4.5 earthquake at a shallow depth of just 10 kilometers beneath the surface of southern Iran, and that number, 10 kilometers, is not a footnote. It is a warning written in the language of physics that every person living between Hormozgan Province and the Strait of Hormuz needs to understand right now. Shallow earthquakes do not simply shake the ground. They deliver their full energy directly upward into the structures, the streets, the unreinforced brick walls, and the lives of the people standing above them. When a seismic event is rooted at 10 kilometers depth, there is almost no rock buffer to absorb the shockwave before it reaches the surface. What travels up is nearly everything that was released below. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: USGS, NOAA, the Smithsonian Global Volcanism Program, NASA, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public. The responsibility to check belongs to all of us. But that is not even the complete picture, because what the data from today's event in southern Iran actually reveals, when it is placed inside the full geological context of this region, is not simply a moderate tremor on a Tuesday in May. It is the latest pressure signal from one of the most tectonically loaded fault systems on the surface of this planet, a system that has already demonstrated, in the historical and geological record, exactly what it is capable of doing when the stress it has been accumulating finally finds its release. The earthquake recorded in southern Iran on May 13, 2026 is not an isolated event, it is a communication. And understanding what the system is communicating requires traveling backward through time to when this belt of mountains was being built, and forward again to the present moment, where the instruments are showing a pattern that scientists in the region choose their language carefully when describing. That careful language is itself the warning. Southern Iran sits on one of the most consequential tectonic boundaries anywhere on Earth. Beneath the surface of Hormozgan Province, beneath the ancient trading port of Bandar Abbas, beneath the fishing villages strung along the coast of the Strait of Hormuz, two of the planet's largest tectonic plates are in direct collision. The Arabian Plate, carrying the floor of the Persian Gulf and the landmass of the Arabian Peninsula, is moving northward at a rate of approximately 223 centimeters per year. 223 centimeters, the length of a thumbnail, the width of a finger. That is the annual distance this plate moves. It sounds like nothing. It sounds like a geological measurement so small it could not possibly matter to a human being going about their daily life. But understand what that movement means when it has been occurring without interruption for millions of years, and when the plate it is driving into the Eurasian plate does not yield easily. The energy that cannot escape as slow, continuous movement must be stored. And the structure that stores it is the Zagros fold and thrust belt, a mountain range built entirely from compressed rock, and one of the most seismically active zones on the surface of this world. The Zagros fold and thrust belt extends approximately 1,800 kilometers from southeastern Turkey to the Strait of Hormuz. It accommodates, according to published peer-reviewed research from the Geophysical Journal International, roughly one-third of all the convergence between the Arabian and Eurasian plates along the southern edge of the Iranian plateau, one-third of a continental collision concentrated into a belt of mountains and the fault systems that lie beneath them. The main Zagros reverse fault and the mountain front fault are the primary structures along which this energy moves. But beneath them, and cutting diagonally through the central portion of the belt, lie the strike-slip fault systems, most notably the Kasran fault system, a right lateral fault zone in the middle of the Zagros seismogenic zone whose documented history of seismicity includes fault interactions, stress migrations, and the kind of seismic sequencing that seismologists describe in their careful language as a system that is accumulating. The system is not inactive, it is accumulating. What the official data actually shows is that southern Iran is not experiencing a period of unusual calm punctuated by occasional tremors. It is experiencing a period of continuous, low to moderate seismic signaling that has been maintaining pace throughout 2026, in the 30 days leading up to today's date. Seismological trackers have recorded 16 earthquakes in the Iran region, with 8 of those occurring in the single week prior to May 13, magnitude 4.6 on May 6, east of Hajiabad, Hormozgan Province, at a depth of 10 kilometers, magnitude 4.5 on May 4 in southern Iran, magnitude 4.8 on May 4 in eastern Iran, magnitude 4.4 on May 9, magnitude 4.3 on May 12, 59 kilometers east of Tehran at a shallow depth, and then within hours of midnight crossing into May 13, a magnitude 4.6 earthquake striking the Tehran-Mazandaran border zone. An event felt across the northern capital, prompting the Iranian Red Crescent Society to place all relief bases and emergency response teams on full alert. 8 earthquakes in 7 days, each one shallow, each one a data point, taken individually, none of them cross the threshold of catastrophe. Taken together, they describe a system under load, and here is where this account becomes genuinely significant. Because the people who study this belt professionally, the seismologists at institutions including the International Institute of Earthquake Engineering and Seismology in Tehran, the researchers whose work appears in publications like the Bulletin of the Seismological Society of America, do not look at a cluster of magnitude for events, and conclude that the energy is being safely released in small, manageable increments. The science of seismic hazard analysis does not support that comfort. What research on the Zagros system has documented is something far more unsettling. The temporal patterns of seismicity in this region follow a cyclical structure, with active periods containing moderate to large earthquakes at short intervals alternating with periods of lower activity. The instruments are showing an active period. The question is not whether larger energy release is possible in this system. The question is when. To understand the full weight of that question, it is necessary to go back to June 21, 1990, 36 years ago. Northern Iran, not southern Iran, but the same nation, the same tectonic collision, the same Arabian plate pressing northward into the Eurasian plate at 30 minutes past midnight local time, when the population of Gilan and Zanjan provinces was asleep inside their homes, mud brick homes, unreinforced masonry structures that had sheltered families for generations, a magnitude 7. For earthquake ruptured along an 80-kilometer segment of the Rudbar fault within the High Alborz seismic belt. This is not a hypothesis. His is documented in the geological record. This is preserved in the rock, in the data archives of the United States Geological Survey, in the field reports of international relief agencies that arrived in the days that followed to find a landscape of collapsed villages. The Manjil-Rudbar earthquake of 1990 devastated a zone of 20,000 square kilometers. A 20,000 square kilometer area of devastation larger than the combined footprint of the cities of London, New York, Los Angeles, Tokyo, and every city in between. Between 35,000 and 50,000 people were killed, not estimated, not projected, confirmed within the range by the National Geophysical Data Center, by the United Nations Disaster Relief Organization, by Iranian government reports filed within 24 hours of the event. Another 60,000 to 105,000 people were injured. More than 400,000 were rendered homeless in the middle of the night. In June, in the mountains of northern Iran, in towns along one 80-kilometer stretch of the fault rupture, every single building was reduced to rubble, and a significant portion of the residents did not survive. In Rudbar alone, an estimated 6,000 people were killed and 10,000 injured in a single town. The following morning, a magnitude 6.5 aftershock struck the city of Rasht, breaking a dam and sending floodwaters across farmland already buried under landslides. One of those landslides displaced 20 million cubic meters of material, 20 million cubic meters, which is a number that requires translation. That is enough displaced earth and rock to fill Madison Square Garden more than 12,000 times. That is what one landslide looked like, and the earthquake that triggered it registered 7, for on the moment magnitude scale. The fault that produced the 1990 Manjil-Rudbar earthquake had not been classified as active prior to the event. That sentence needs to be read again. The Rudbar fault, the fault that killed up to 50,000 people in a single night, had not been formally identified as a seismogenic threat before it ruptured. Published research in the Bulletin of the Seismological Society of America notes this directly. The system of surface faults on which the earthquake occurred had not been deemed active before the rupture, leading seismologists to conclude that return periods for this class of earthquake in Iran may be long enough that a given fault can complete its entire accumulation cycle without generating an event that the modern instrumental record would flag as a precursor. In other words, a fault can be silent for generations, building stress without a single tremor visible to modern instruments, and then deliver its entire accumulated energy in a single catastrophic rupture. This has already happened once. The record of it is still preserved in the rock. Now consider the southern Zagros. Consider Hormozgan Province. Consider Bandar Abbas, a city of approximately 750,000 people, the largest container port in Iran, home to major naval facilities, positioned at the throat of the Strait of Hormuz, through which an estimated 20% of the world's traded oil passes every single day. Consider what the probabilistic seismic hazard data actually shows for this city. Research published by Iranian seismologists and cited by the Iranian Code of Practice for Seismic-Resistant Design of Buildings identifies Bandar Abbas as having the maximum peak ground acceleration value in the entire country for the 475-year return period, a value of 0.35 grams, tied only with Tabriz in the northwest. What does that mean in practice? It means that the best available scientific models of seismic hazard in Iran identify Bandar Abbas as the single most exposed major urban center in the nation to ground acceleration from earthquakes. The people of Bandar Abbas, the 750,000 people who wake up each morning in this city on the Persian Gulf, who go to the port to work, who send their children to school in buildings whose construction was not universally governed by earthquake-resistant design standards, live above one of the most stressed fault systems on Earth, in a city that official hazard assessments rank as the most seismically exposed urban center in Iran. Imagine being one of those people. Imagine sitting in a coffee shop in the old quarter of Bandar Abbas on a morning in May, feeling a brief shudder pass through the floor, one of the 94 earthquakes per year that historical data says this area experiences on average, another magnitude 3 or 4 event, barely worth mentioning. Now imagine that the coffee shop you are sitting in was built with unreinforced brick. Research on building vulnerability in Bandar Abbas, published through academic and engineering institutions, identifies the older areas of the city as having both the highest seismic hazard and the highest concentration of vulnerable structures, the same combination that was present in Rudbar in 1990. The older areas of the cities are expected to suffer the highest amount of damage, and the highest seismic hazard occurs in these areas as well. That is what the official seismic vulnerability assessment of Bandar Abbas states. It does not state this as a prediction. It states it as a measured fact about existing conditions, and Bandar Abbas is not alone. Across the Hormozgan coastline through Bandar Kamir, Bandar Lenga, Minab, and the smaller fishing settlements that have stood on this shoreline for centuries, the same pattern of vulnerable construction meets the same geological reality. Since 2025 alone, the Bandar Abbas region has recorded 40 earthquakes of magnitude 2 and above within 100 kilometers. In July 2022, a doublet earthquake struck Hormozgan Province, two separate magnitude 6.0 events occurring within 2 hours of each other along the Zagros fold and thrust belt. 7 people were killed, 111 were injured. The strongest aftershock measured 5.7. This is not a historical precedent from a century ago. This happened 4 years ago. The same province, the same fault system, the same coastline. The 2022 Hormozgan doublet deserves its full weight in this account. A doublet earthquake, 2 separate main shocks in rapid succession, is not a common occurrence. It represents an unusual and scientifically significant release pattern in which the initial rupture of a fault transfers stress laterally along the belt rather than simply releasing it downward into deeper rock. This is the mechanism by which seismic energy migrates. A magnitude 6.0 earthquake occurs, and the static stress it generates is redistributed along neighboring fault segments that may already be near their own failure threshold. The Kazran fault system in the central Zagros has been specifically studied for this migration pattern. Research documented in peer-reviewed literature shows good evidence of fault interactions and seismic migrations along this system, meaning that energy released at one point along the belt does not stay at that point. It travels. Minutes are not hours, and in this context, that difference is everything, but in the geological framework of stress migration, hours are not years either, and between a moderate earthquake cluster and a major rupture, the timeline can compress without warning. This connects directly to a second global system that the science of seismic hazard analysis asks researchers to consider alongside tectonic loading, the role of surface loading and unloading processes in modulating stress on active fault systems. The Persian Gulf, which borders southern Iran along its entire southern coastline, has experienced documented changes in sea level and water mass distribution in recent decades. Ocean temperature anomalies in the Gulf region have been recorded at levels that affect both water volume and the gravitational loading pressure on the seafloor crust immediately adjacent to the Zagros coastal fault systems. Research into gravitational loading and volcanic chamber pressure has been conducted elsewhere in the world, but the same physical principle that changes in the mass distributed above a fault system alter the normal stress on that fault applies in principle to the Zagros coastal zone. While no single institution has published a definitive paper establishing a direct correlation between Persian Gulf thermal expansion and the precise timing of Zagros coastal earthquakes, the broader framework of fluid-induced seismicity and loading-modulated fault behavior is established science, documented in peer-reviewed literature from multiple institutions, and the direction of its implications for southern Iran is not reassuring. There is a third connected system that operates at a scale the eye cannot see but the instruments do not miss. Solar activity and its influence on Earth's ionosphere and upper atmosphere has been studied in relation to seismic events in a body of research that remains contested. The scientific consensus does not yet establish a causal mechanism, but what is documented without dispute is that the ionosphere above seismically active zones shows measurable anomalies in the hours and days preceding major earthquakes. Whether this is a cause, an effect, or a coincident signal of deeper crustal processes remains a question that instruments are currently trying to answer. What the data from space weather, COM and NASA monitoring networks shows in the current period is an elevated level of solar-wind interaction with Earth's magnetosphere. The connection between solar forcing, ionospheric loading, and fault behavior is, as scientists choose their language carefully to say, an area of ongoing active research. That careful language is not dismissal. It is the acknowledgement that the system is not fully understood, which is a very different statement from the assurance that there is no connection. Return now to the present. Return to southern Iran. Return to the specific data that is in front of us today on May 13, 2026. The magnitude 4.5 earthquake that struck at shallow depth in southern Iran today is the most recent event in a sequence that, over the preceding 10 days, has generated magnitude 4, 6, 4, 5, 4, 8, 4, 4, 4, 3, and 4, 6 events across the Iranian plateau and its southern margin. 8 earthquakes of magnitude 4 and above in 7 days, each one shallow. Each one a release of seismic energy that, while not catastrophic on its own, represents the system communicating its state. The system is not inactive, it is accumulating, and the historical record of this same fault zone, reaching back through documented events to the deadliest earthquakes in the modern history of this nation, shows what accumulation eventually produces. Here is what the science of probabilistic seismic hazard analysis does and does not say. It does not say that a major earthquake in southern Iran is imminent. Precise prediction, with a date and a magnitude and a location specific enough to evacuate a city remains beyond the capability of every seismological instrument and every computational model that exists on Earth today. This is not a failure of science. This is the nature of a chaotic system operating on timescales that human instruments have only been monitoring for a fraction of one seismic cycle. What the science does say what it says with the full weight of probabilistic hazard modeling, historical cataloging, and structural analysis of the Zagros belt is that the potential for a major earthquake in southern Iran is not theoretical, it is not speculative. It is a quantified probability attached to a real fault system carrying real accumulated stress. The question is not whether the Zagros fold and thrust belt is capable of producing a magnitude 6, 5 or 7, 0 earthquake in Hormozgan Province. The geological record has already answered that question. The 2022 doublet demonstrated the answer 4 years ago. The 1990 Manjil-Rudbar earthquake demonstrated what happens when Iran's faults deliver their full accumulated energy in a single night. The question is only when. Think about the 750,000 people in Bandar Abbas again. Think about what a Tuesday morning looks like in that city, the port workers arriving at the loading terminals, the boats in the harbor navigating the warm waters of the Strait of Hormuz, the school buses moving through narrow streets between old buildings in the historic quarter, the families in apartments that overlook the Persian Gulf drinking tea before the day begins. These are not abstractions. These are people living inside a hazard map that their own government's engineering codes identify as the most seismically exposed urban location in Iran. If those people had access to the full seismic hazard data right now, the probabilistic models, the historical death tolls, the vulnerability assessments of their own buildings, the sequence of shallow earthquakes recorded in their province over the past 30 days, they would be asking one question with urgency. What is being done? The answer, as with virtually every seismically exposed city on Earth, involves a complex and unfinished mixture of updated building codes, preparedness plans, early warning system development, and the slow, difficult, enormously expensive work of retrofitting structures that were built before seismic risk was. Formally understood, the work is underway. It is not complete. It has never been complete anywhere in the world before a major earthquake has struck. The 2003 BAM earthquake in southeastern Iran's Kerman province is the other date that belongs in this record. December 26, 2003, a magnitude 6.6 earthquake struck at 1:56 in the morning local time in a city of 142,000 people, more than 70% of whom were asleep in mud brick and adobe structures. In less than 12 seconds of shaking, more than 26,000 people were killed. 26,000 people in 12 seconds. The entire historic citadel of Ar-Gibam, one of the largest mud brick structures in human history, a 200-year-old fortress that had survived conquests and empires and the accumulated weight of 20 centuries, collapsed entirely. The fault that produced the BAM earthquake was not well mapped before it ruptured. The return period for earthquakes of that magnitude on that fault was estimated to be long enough that the city had not experienced a comparable event in living memory or the memory before living memory, and yet the rock remembered. The stress had been building invisibly without expression in any instrument until the morning of December 26, 2003, when 12 seconds of shaking extracted a price that no accounting can fully calculate. This is the geological reality that the magnitude 4.5 earthquake in southern Iran today must be understood against. Not as a disaster in itself, it is not as a certainty of future catastrophe, it is not that either, but as a signal from a system that has demonstrated in the verified historical record exactly what it is capable of producing, the Zagros fold and thrust belt is one of the most seismically active structures on the surface of this planet. The Arabian plate is moving northward at 2 to 3 centimeters per year and has not stopped. The accumulated convergence that does not find expression in gradual surface creep must find expression somewhere. The instruments record where it has been finding expression in 2026, 8 earthquakes of magnitude 4 and above. In 7 days, in a zone whose seismic hazard models rank among the highest in the world, what the official data actually shows is a system in motion. Not a system about to stop, not a system that has found its equilibrium, a system in which the energy released by each moderate earthquake may redistribute stress along fault segments that have not yet spoken, segments like the unnamed fault near Rudbar that produced no seismic signal prior to June 21, 1990, and then killed up to 50,000 people in a single night. The Kazran fault system in the central Zagros shows documented patterns of seismic migration. The mountain front fault along the southern margin of the Zagros carries accumulated reverse fault stress. The Makran subduction zone in southeastern Iran, where the Arabian plate is being driven beneath the Eurasian plate at depth, carries the additional capacity for tsunamigenic earthquakes that would reach the coastline of Hormozgan Province within minutes of a major rupture offshore. Minutes are not hours. The Makran subduction zone produced a devastating tsunami in 1945 that killed an estimated 4,000 people along the coasts of Pakistan, India, and Oman. A comparable event today would meet a coastline whose population density has grown significantly in the 8 decades since that event, and a Strait of Hormuz whose shipping traffic represents a significant fraction of the global economy. This is not speculation. This is the documented behavior of the system, and the system has not changed. The subduction continues, the stress continues, the data continues. There is something that must be said plainly here, with the same authority as every verified number in this script. The science of earthquake monitoring has never been more advanced than it is in May of 2026. The instruments are sensitive, the networks are dense, the data is processed in near real time. And yet, for all of that capability, the honest statement from every seismologist who has studied the Zagros belt is identical in its essential content. Detection is possible, monitoring is in place, and prediction is not. Precise, actionable prediction of the time and location and magnitude of the next major earthquake in southern Iran or anywhere else on Earth remains beyond the reach of current science. That is not a reason for despair. It is a reason for preparation. For retrofitting, for early warning systems, for building codes that are written and enforced, not written and filed, for the kind of institutional seriousness about seismic risk that translates the data on a probabilistic hazard map into structures that stand rather than collapse, and into populations that know what to do in the seconds after the ground begins to move. The people of Bandar Abbas and Minab and Bandar Kamir and the fishing settlements of the Hormozgan coast deserve that seriousness, not as a favor, not as charity, as the straightforward application of what the data shows. The data shows that they live above one of the most seismically active fault systems on Earth. The data shows that their buildings, particularly the older structures in the historic districts of coastal towns, carry the highest vulnerability to the ground acceleration that the probabilistic models assign to this region. The data shows that southern Iran has recorded at least 293 major nearby earthquakes in 2026 alone, that the Bandar Abbas region averages 94 seismic events per year, and that a magnitude 6 or greater event occurs in the area approximately once every 12 to 13 years based on the historical record. The last magnitude 6 class earthquake near Bandar Abbas was the 6.4 event of November 2021. The last magnitude 6 class event in the broader Hormozgan region was the 6.0 doublet of July 2022. The historical average is running, the system is not inactive, and so the seismograph records a magnitude 4.5 in southern Iran on the morning of May 13, 2026, at a depth of 10 kilometers, on a fault system that accommodates one-third of a continental collision in a province where the probabilistic seismic hazard model produces the highest peak ground acceleration value in the nation. In a region that has not experienced its full seismic potential within the span of any living person's memory, which is precisely the condition that seismologists recognize as a long recurrent system carrying unspent energy, the same condition that was present in Rudbar before June 21, 1990, and in Bam before December 26, 2003. There are 172,300 people documented to have died in Iranian earthquakes since 1950 alone, 172,300 people. That number exists in the official record. It exists because the ground moved and the structures above it were not built to remain standing when it did, and the populations inside those structures had no seconds of warning before the energy arrived. Every single one of those deaths is a data point in the hazard analysis that seismologists use when they study the Zagros belt today. Every one of them is evidence for what the system does when it reaches its failure threshold. And every shallow 4.5 magnitude earthquake recorded today, every cluster of moderate events in a 7-day window, every new seismic signal from a fault system that has been accumulating stress since before the first instruments were placed to listen for it, every one of those is the system communicating, not shouting, not yet, but speaking in the precise numerical language of seismic waves in a frequency that the instruments are designed to hear. The Arabian plate moved approximately 2 to 3 millimeters in the time it took to read this sentence. It has been moving at that rate for approximately 25 million years. The mountains of the Zagros were built by that movement, lifted, compressed, folded, fractured, and raised again over timescales so vast that the entirety of human civilization, from the first cities of Mesopotamia to the port facilities of Bandar Abbas today, occupies less than the final half-second of that geological clock. The fault system beneath southern Iran does not know that we have built cities above it. It does not know about the port or the shipping lanes or the 750,000 people who have made their lives on its surface. It knows only stress and the threshold at which stress becomes rupture. And on May 13, 2026, the instruments placed by human science above that fault system recorded another communication. From the depth of 4.5 magnitude signal, shallow, precise, and part of a pattern that the geological record has already told us, in the most unambiguous terms available, how it ends.